It's 3 o'clock Central European time here. Welcome everybody to this webinar from Taiwan Semiconductor about low and medium voltage MOSFETs here. When the last people are probably now just dialing in, so I'm just going to go through a few housekeeping rules here while showing the agenda here. So you will, after the presentation, you will get an email here. You can actually ask for the presentation, or after the webinar, you will get an email. You can ask for the presentation. Also, the presentation will be recorded. So if you think this is interesting for a colleague, you can ask also for a recording here. That's also not a problem. You can also follow us via LinkedIn to keep up to date about what we are doing here. And you can also subscribe to our component engineering newsletter. I think the webinar will last about 45 minutes. That's the target here. There will be a Q&A session afterwards. There is actually a button on your screen where you can put in the questions here, and afterwards we will actually try to answer them. If you don't get an answer today, or if we miss your question, don't worry. Actually, all questions are recorded here, and then you will get a follow-up email tomorrow. So you can see the agenda here. We advertise the webinar via Bodo's system, power systems here. So maybe not everybody knows us. So we're going to talk 2 minutes about our company, not more. Then we're going to talk about MOSFET technology. Then I think a lot of people had some issues on the supply chain of MOSFETs the last 3 years. So we actually want to explain it also to you, so you get a better feeling what it takes to make a MOSFET and how you can build up a MOSFET supply chain here. We're going to talk a little bit about our product range and also about applications information. So here we go, the slide about our company here. We founded 40 years ago, more than 40 years ago, maybe while you are reading this slide here. We're also more than 20 years in Europe. We have an office in Munich where we have sales and customer service, but we also have a logistics specialist and actually an automotive quality specialist and some other functions that you need. If you're curious to learn more about the financial of our company, we are traded on the stock exchange in Taiwan, so nothing is a secret there. You can read about it all. If you do so, then please note that the company consists of two parts, a printer division and the semiconductor division here. And we're going to reach about together $500 million. So we're not a giant, but we're not that small either. The semiconductor division here has 4 production sites and 16 worldwide sales offices here, so we can support your demands worldwide. We are known in the business as a rectifier company, and there I would say that we do offer a comprehensive product portfolio here with all the products, or 95% of all part names in rectifiers and bridge rectifiers. Whether you're talking from standard rectifier here to a Schottky rectifier, where you're sitting in the second group here, to, of course, we also have the whole product range of TVS. We're investing quite a bit on TSC diodes in arrays these days, so that's an area of expansion for our company. But then, apart from the rectifiers here, we have 3 big design teams, one for MOSFETs, one for linear voltage regulators, and one for lighting ICs. Today, we're going to talk about the MOSFET business of our company. We are in MOSFETs for over 10 years. We released the first ACQ101 MOSFETs in Q2 2020 using a standard trench process. We have a strategic alliance with UMC, the foundry in Taiwan. TSC has been working, or its design team has been working on split gate technology for several years now. We introduced the first 40-volt split gate MOSFETs in Q2 2022 for the industrial market. We will introduce the automotive versions for that in Q1 2023. And of course, we're expanding our products with new packages and products in the whole of 2023. The webinar will focus on the last 2 parts here, the 40-volt split gate technology here. And then, of course, what we are doing in the future. Let's talk a little bit about MOSFET technology. The next slide is actually here. I am 61, so I grew up with planar MOSFETs, so I don't ignore them or make them hide or anything like that. So they've been around for a long, long time. They are still around. The webinar is more about the medium voltage and low voltage here, what you see here. They're still around in high voltage, but also in small signal products like the 2S7002 in many cases. So it's a robust product here. It's got a big die, so it means it's got a good avalanche capability, and it's got great EMI. they're not finished yet here. We're focusing today more on medium and lower voltage MOSFETs here. You'll be surprised here that trench is actually already in the market in mass production for close to 25 years now here. So this is the first time when we started to parallel all these gates here to get a lower RDSON here. That was the initial advantage of trench here, and in the meantime also it now became a very cost competitive process here. We've been pushing this trench actually here to the limit here. We have here something called thick bottom oxide, which is the bottom of the thick trench gate, or shallow gates, shallow trench, and things like that. So we've been tweaking this process to the end here to further reduce the RDSON and also to reduce the QGD. So we have lower switching losses here, and we've also optimized the cost of this process here. So we've been pushing that for the last 20 years, but somewhere we reached the limit. And if you want to go to big die, you know, and lower RDSON MOSFETs here, you need to go to split gate here with the split here, meaning this bit here. We'll talk a little bit more about that here, which is actually giving you the lowest RDSON per square millimeter possible in the industry, a very low QGD and a built-in RC snuffer here. So this is the history of the MOSFET processes over time. And of course, today we're going to talk about a new split gate MOSFET process. Before that, we're going to have a quick look at the cell here. And I'm going to start here at the bottom left of the figure here, where you see all these MOSFETs in parallel here. So we have the RGs, you know, all the what they call the gate runners here. So all these MOSFET cells here, we're talking about 100,000 here, depending on the die size here. So it's pretty substantial here. Then we have the drain and the source terminal here, and we have all these parallel cells here. You don't go to the right here, what it's all about is we're paralleling all these MOSFETs with to get a lower RDSON. But the unfortunate fact is, if you parallel things, the RDSON goes down or the resistance goes down, but unfortunately all the capacitance goes up, and that's where all the tricks have come in to you know, improve the MOSFET technology. The figure here, the top left one figure here, I've always want to point out to people that is not to scale, because you get a lot of people that look at this MOSFET here. You have to think of a MOSFET die of something like 100 micron thickness here, and this is a few micron here. So this is only a small percentage of the the depth of the micron of the MOSFET die, if you wish to. And if we're going, the drain is at the bottom. If we're going from the drain to the source here, we're seeing that we first have the package resistance here, then the substrate, the epi, the epitaxial layers, and then here what we call the channel. The channel is here where the p-poly is inverted here. So that is actually the composition of the resistance of a MOSFET here, and we're putting these channels here in parallel here. And be aware that actually this bit of the MOSFET is 50 times bigger, let's say, than this bit of the MOSFET here to put things in scale here. So we have a MOSFET here because of this trade-off here between RDSON and capacitance. We're measuring something like QGD multiplied by RDSON to get a balance or a feeling of the process, you know, how much it, you know, the switching losses will contribute versus the RDSON losses. And the multiplication gives a good idea about the quality of the process. This is something everybody can read in the datasheet. However, if you talk about RDSON per square millimeter, this is not something you can read in the datasheet. Of course, that gives you an idea of the cost structure. What is the RDSON per square millimeter? So that's another parameter which we keep secret. So let's look at the RDSON actually and the trade-offs here. So if we go to this slide actually here let's talk about this RDSON per square millimeter to give you an idea. It is actually different for every voltage. So we've got 40 volt MOSFETs here, but it will be different from 30 volts or 100 volt MOSFETs. And what you need to realize is that it works like this. Let's assume a number and let's make it easy so we can do the maths all together without you know, getting a headache here. Let's assume that we have something like 10 milliohm per square millimeter for this 40 volt process, which is not such an unrealistic number here. So how does this work? So a 1 millimeter die is 10 milliohm. 2 milliohm die you need, or 2 square millimeter die, you get 5 milliohm, and so on. 4 square millimeter, you get 2.5 milliohm. 5 square millimeter 2 milliohm, and 10 square millimeter 1 milliohm. So that's how the die size goes up with the RDSON. Of course, there are other things, right? So like the package set off there. You have yields which are worse at bigger die. You of course the CPKs and distributions here. So it is a simplification here. But as the die size goes up, the RDSON goes up. Of course, the current you can put through the dies also goes up. We also know that you're going to put more cells in parallel, so the capacitances go up. The bigger the die, the better the avalanche capability. So you can push more through it in avalanche energy here. And of course, the cost of the die will also go up. Now, let's go a little bit more on how you can improve this RDSON here per square millimeter here. And we're going to the bottom here, where you see that, if you remember from the last slide, we're not doing the package here, but the substrate makes a contribution here, the epi makes a contribution to the RDSON, and the channel makes a contribution here. And as you go to higher and higher voltages, the epi becomes more and more important, because that is linked in a standard trench process to the breakdown voltage here. So now we're going to try to make the RDSON better here. So we're going to go from the bottom to the top here. The bottom here says change the source wire to copper clip. So if you make the RDSON of the package smaller, then of course you improve the RDSON of the whole MOSFET here. The second one is, we noticed on the last page that the substrate or that the things are not to scale here. So the substrate is actually an important contributor here, especially in the low voltage MOSFETs here. So if you make them thinner, then you can also reduce the RDSON here. Making the MOSFETs thinner here is a process called back grinding, or sometimes abbreviated by BG. So if you hear the word back grinding, that's another word for making the wafer thickness or the wafer thinner here of the MOSFET here. This actually is not a clean process here, and it increases the wafer cost. And of course, you can't do it in a standard fab. And then, of course, we do the same with the copper clip. Of course, that increases the manufacturing complexity here. So those two things, come at a cost here, but for bigger die, the advantage outweighs the higher cost here. Now we're going to look at the channel here, and the two things here. It says here, the decrease the channel length. That's just a trick. We're not going to talk about that. That's just internally how you make a MOSFET process here. But let's talk about this cell density here, because that's actually important also for the supply chain here. So the cell pitch here is the distance between those two gates, the two gates here. And then of course you have the minimum feature size to diffuse all these things here. This will be determined by the lithography here of the process here. So if you have increased the cell pitch and put them all closer together and make everything narrower so that you can make a finer process here, you can increase the cell density. You can put more in gates in parallel here, so more lower RDSON of course here, but you increase the capacitance here. The distance here is the cell pitch, and the smallest minimum features determine the lithography used here. So now we're going back here to increase cell density here. So we know the switching times are increased because the capacitances are increased here, but the lithography used is different here. And that is a factor that has been causing a lot of questions and maybe pain over the last 3 years in the MOSFET market here. And we'll talk a little bit more about that in supply chain. But you need to understand that this determines partly the cell pitch and is a key feature to reduce the channel on resistance. So now we're going to look at the advantages of split or shielded gate technology. On the left, you see the NP series, which is our standard series of the range. And here you see the split gate MOSFET here. The first thing that actually confuses people is the name split gate technology or shielded gate technology. They wonder what this bump is actually here under the gate. It's actually not a second gate or anything like that here. This is connected to the source potential. That's something you need to understand. If you look carefully at the last slide, actually, you saw that we did everything. We worked on the thickness of the wafer. If you remember well, we looked at the packaging resistance. We tried to increase this channel, the channel by putting more in parallel and that type of stuff. But nobody actually worked on the epi here, on the epi resistance. Now the epi resistance here in standard trench, there's not that much you can do about it. This is the drain, this is the drain here and the source on the top, of course. And if you have 40 volts, actually the breakdown field is on this area here. So the resistivity of the epi, actually, it determines the breakdown voltage. So this thing you can't manipulate here. So that actually is one of the things the shielded gate or split gate technology does here. This is potentially connected to the potential of the source, and it actually manipulates the drain source field here, so you can use lower epi resistivity here. So you get a increase here in two ways here. You get not only the lower RDSON here, but if you see here, this is the gate, this is the drain here with the capacitance here. It's also here, the CCGT, also that is reduced here. So you have a double whammy here on the technology here, which includes, of course, a better figure of merit, QG, RDSON. So we're doing all this work and making these dies smaller and better RDSON per square millimeter. What do you see actually in your scope plots or in your design? It's going to be on this graph here. It's going to be that the Miller plateau here is you're going to travel to the Miller plateau much faster here. You're going to have much better switching speed, and you're going to have lower switching losses. That's what you're going to see in your scope plots and in your designs here. What's behind this here with this improvement of the RDSON per square millimeter is not something you may notice here. You may notice in the specs here on things like thermal resistance and that type of stuff. The last thing I want to point out here is that you have this CDP here, drain to this thing connected to the source here. So in parallel here, you have an RC network here, which is an RC snubber. So you'll have less overshoots on the drain source here, voltage spikes here. That's another advantage of this shield gate technology here. Is something you need to know here. We've also got one gimmick here. It's called the PerFET. We have a trade name here. So we call our technology the PerFET here. So that's something we want you to also remember. So here we are. We're using the PerFET now in the 40 volts here, NH here. So something internal here which you need to notice. NB here is the old trench series we had. NH is the split gate trench series we have. So the first thing we're going to do here on the left hand side is look at logic level MOSFETs and see the ratio between the RDSON at 4.5 and 10 volts. So here we clearly have with the new series an improvement here which will benefit you. The second thing graph here in the middle is QG and QGD. This we already spoken about in the last slide here. So there are substantial decreases in QGD if you go to split gate technology here. The third one here is increase the threshold voltage minimum and have a better distribution here. We're going to talk a little bit later on that when we talk about driving motors and in MOSFET bridges here. So this one going from 1.1.4 volt will give you better immunity against inductive turn-on by accident here, and having a lower spread in the threshold voltage and a smaller distribution here will actually allow you to more easily parallel the MOSFETs here. The fourth advantage of our new series, the NH series here, of course, every MOSFET has an RDSON that has a positive temperature coefficient. And this temperature coefficient is lower for our new series, the NH series, which gives you additional benefits, especially if you're working at high junction temperature. The last thing is about wet wall flanks, and we've got several slides on that. So I'm not going to go into detail here, but our new PerFET family will always have wet wall flanks, either it's industrial or automotive here. And that's something we'll explain in a later slide. Okay, well, who hasn't had MOSFET delivery problems the last 3 years, right? And maybe there are not enough suppliers in the market. Here is one of it, and there are some other issues also on the supply chain here. So we're actually happy to enter here and give you a little bit more explanation how this works in the supply chain. So what you see here is split always, the supply chain is always split between the front end and the back end. So we're looking at our split gate technology is a 6-mask process or a 6-layer process. what, you know, some people have this rule of thumb in the industry saying that actually there is like 1 week per mask, something like that. Well, actually, ours here, if you look at mask ones, where we etch all these deep trenches and that type of stuff, you know, our first mask is a little bit more complex than the average mask, let's put it like that. So we're looking at a cycle time, or not a cycle time, or, you know, typical lead time of 8 to 9 weeks in the front end here to make this, to make our wafers here on our 8-inch wafers here. So that is the first step we're doing now. We're doing this at UMC. We'll talk a little bit more about UMC too, which is our front end and our partner. At after wafer fabrication, you need to probe the wafer here, which is take another 1 or 2 weeks here. Then we have this BG/BM. Remember, I told you BG stands for back grinding and BM is for backside metallization. So first you make the wafer thinner, and then of course you have to apply the backside metal again. So that is a process that is not so compatible with a clean room, let's put it like that, and as a result, that is also an external process of about 2 weeks' time here. Then you go to the assembly. As you can tell here, we'll talk a little bit later about that. We're using aluminum ribbon bonds here with a stitch here to assemble on the die here, and then of course you need to go to test marking, testing and taping here. So this step is about 3 weeks and then another 2 weeks. So in the end, you're talking about roughly lead times of 16 weeks. Which you can work together, of course, always with the supplier by having the wafer ready via forecast or all kinds of agreements here. So this is more or less what our cycle time looks like here on the front end here. On the back end, I should tell you that is on the PDFN 5x6. We are investing in our own capacity here, so we build up our own back end on PDFN 5x6, and we're using one subcontractor. So we have a dual back end. The front end is on UMC. A little bit more about UMC. So UMC is not just our front end, but it's also a partner and investor. So they invested in our company and sit on our board. So one of the board of directors is a member of UMC here. To understand this graph, and this is just a copy of their 2021 financial report, you need to go counterclockwise. So let's go to the figure of 2021 and go counterclockwise here. You have 0.5 micron process, which is quite old here, 0.35, 0.18, and then you go like this, and this, like you go like that from old to new here, with the investment predominantly going to the newer process. What happens is people, digital ICs, some power management ICs, become more and more complex. So they benefit from going to a smaller lithography. So gradually this capacity becomes free, and more ICs move to this lithography here. Rather than closing factories or actually not using this capacity, they are perfect to use MOSFETs here. So for the older people here on the call, I mean, we used to hang out with trench MOSFETs of 1.3, but even 0.5 now is actually a very outdated process for MOSFET. So we are actually in this area at the moment. 0.16 is our process here. So this is the area we are utilizing. Potentially you could use this level MOSFETs in this area here. So this is the area where more capacity becomes free here, and that will be perfectly used for MOSFET here. So MOSFET are designed on these nodes here. You know, the 14 nanometer node is especially notorious, and these nodes, some of these nodes for allocation here. So we are designing on these nodes here. UMC, this is from their third quarter results. 2022 had 2.5 million or 2,539,000 8-inch wafers. That is 8-inch equivalent wafers, so 12-inch converted to also 8 wafer capacity here per quarter. So even 1% of that is 25,000 wafers. That's just to give you an idea. So 25,000 wafers in a quarter would easily give you a MOSFET revenue of about $20–25 million here. So that's how big UMC is. I think they're the second biggest foundry in Taiwan and also one of the top foundries in the world here. So analog and other ICs move to smaller lithography. Capacity becomes available on the MOSFET nodes, and this is what we call a win-win situation here. And that's what we're also messaging here, that we're in this business for the long term, not long term. Let's talk a little bit about our product range. So this is our product range. I'll let the page settle in here so you can look for it at a second. So the first products released were all 40 volt. This is the industrial range, right? So we're going from 1.9 to 7 milliohm here. We have logic level versions of each part, so the standard level and logic level versions. The maximum currents here are by the package limit here that we explain a little bit later on more about later on here. We already told you about the threshold voltages, that we move them narrower and up a bit here. This is for the logic level. What you see here is 2.4 is 3.6 is then for the standard level here. The QG values are here. You can also look at the QGDs in our data sheet. And this product is rated at 175 degrees C here. So we're having the standard version of the PDFN 5x6 and the dual version of the package here. So with a 7.6 milliohm. We also launched a PDFN 3x3 range with 5.6 and 7 milliohm versions of the 40 volt. Again, logic level and standard level here. The automotive versions of these will have a very similar specs and will be available actually in the in Q1 here. So, but we're already sampling these products here, and we're also have preliminary data sheets here. So we're actually also developing already a lot of products in automotive here. So we are ready to promote this product also for automotive accounts here. So we told you that for our range here, we will use the PDFN 5x6U, the wearable flank package here. So for both industrial and non-industrial or automotive versions here, in this case, the automatic optical inspection is mainly used by automotive customers here during the assembly process to ensure the quality here. So the pins with the wearable flank can improve the solder joint reliability and also the accuracy of the automatic inspection here. So it's the solder joint area is increased by about 55% here. So this is all nothing new to our automotive customers and people working in automotive, but for the people that are working in other fields that are not used to this type of automatic inspection here, we made an application note. Sorry, it's a small print here, but you've got the link here. So it's a 5 or 6 page application note, AN 1009, to explain all the benefits and how this automatic optical inspection works here. So non-automotive people can also become familiar with this subject. The PDFN 5x6 footprint compatibility. There's a lot of things in small print here. Unfortunately, we don't have like the SOT23, which is standardized here. A lot of manufacturers have their own name or product name or whatever market name for the package here. We see TDS on 8, SOT669 or LF pack, the DFN 5x6 or the Power Pack SO8L. You know, so those are all the things that you can see here. Those are all the part names here, or the package name I read to you in a small print, and there's maybe 1 or 2 more here. We checked it all, and our footprints are all compatible, or the footprints are all compatible with each other here. So there's no need to worry about this, but we just need to be aware of all the minor differences of packages in between all these suppliers. The product was launched. This is the product page of our website here. What you'll see on the product page is that we not only give you the data sheet here, but we also give you all the resources here, the SPICE model. The package outline dimensions here are usually also available, of course, on our website. What is new for us is the SNAP EDA cooperation here. We're doing a cooperation now with SNAP EDA for about 6 months, and most of our diodes are available, and of course our new MOSFETs are also available on it. So we've actually converted our entire product line to offer this extra feature and advantage to PCB layout people here. So that's another thing that's fairly new with our company. Yes, to give you 100 slides with all the products we have, it's usually not that exciting, so we'll avoid doing that during this presentation here. But we of course encourage you to visit our website here. This is the link to search for the MOSFETs here. So we're not a company that has thousands of different part names here. We have hundreds. That's our main difference here. But I think we're still an interesting supplier, and of course we are actually growing our business line and our partner lines here. So if you go here, the selection criteria are typical for everybody here. I should say type here is just where you see N or P type. Technology here is where you put in PerFET for the new split gate technology thing, distinguish here, or super junction. You could also use this to look for super junction here. Configuration here is like dual N or NNP, complementary, and that type of stuff. I think the rest of the criteria, search criteria are pretty standard in the industry here. And so our product range does include high voltage planar diodes, super junction MOSFETs, a few of them where we're probably working also on this in 2023 quite a bit here. So we've got a lot of things planned here also in this range here. We have some really popular load switches like in SOL23. We have some small signal products. So we have not a complete, but an interesting product range of MOSFETs, and we do things like load switches in SOL23 rather than have 4 or 5 different versions of every voltage in SOL23. We just have the biggest die and cover the whole market with one here, and hope that the drivers can handle the device. There's a few slides I'm going to show you, though. One is going to talk about packages here, and I think when the webinar is originally about low and medium voltage packages here, and I think here we call all the popular ones. We're going from the right to the left here, the new ones which we introduced here, and we're talking, of course, the dual versions, the PDFN 3x3s, and we have a few products in PDFN 2x2. So these are the more popular packages here for medium to low voltage MOSFETs here. We still have some available here in the middle here. These packages are, of course, replacing the older packages like SOYC8 or TSOL8 here in the future. Also, to a certain extent, the DPAC and the D square pack or TO263. Although it needs to be said here, and that is important to realize, that things like DPAC and D square pack or TO252 and TO263 will be available in the long term, because these exposed packages on the top here actually they do not have the creepage and clearance between the drain and the source here for high voltage MOSFETs like 600 volt MOSFETs. You can't really do in these type of packages. You need these type of packages here to comply with creepage and clearance. So they are not for sure not disappear in the market. They will continue to be there. Here also the True versions, like TO247 here. Super junction will always have fairly big die, or people will push this package here to get more and bigger die in there. And so those packages will also be available, even if it's more for high voltage. The smaller packages here are not just for small signal here, but not everybody reflow solders here. Some people still wave solder here, and these are just good packages and cheap packages also, because they're all depreciated here. So cheap packages here for load switches here. So the SOT23 is doing fine here. We see a lot of applications and demand for it. And the last one here is the most surprising one. I think people dislike this package maybe for the last 30 years. It's still around and it's got a good future, because if you have a smaller high voltage die, this actually offers the creepage and clearance needed for those type of applications here. So the SOT223 here is not dead. It still has a future. So this is more of a short discussion of MOSFET packages here, where of course we're investing most in developing the product in the new exposed path packages here. This is our PerFET family here, what we're doing here in the nearby future here. The first thing is what we have released and the automotive products, which I already mentioned here. This one here is an interesting one when we go back to the technology a bit, maybe here. So our parts are using aluminum wire bonding here with, the ribbons, I should say. This is not wires, this is ribbon bonding here, where they're stitched to the die here. So if you actually move that to the copper clip here, this is about the same die from 1.9 to 1.3 milliohm of RDSON here. So you see the difference is about of the package contribution. is about 0.6 milliohm here. So that's substantial here for a 1 milliohm FET here. If you're doing a 10 milliohm FET, it doesn't really matter. It just adds cost and is maybe not so beneficial here. So at one stage, the extra cost here outweigh the benefits that you get from reducing the RDSON here, or the cost you add, easily compensate for the reduced RDSON here. For every company, this point may be a little bit different here. For us, it's in this area here. So we're actually supplying here engineering samples of these automotive parts. We're also having preliminary specs, and I guess enough simulation data available on the 60 volts. So we are discussing already specs with customers here. So we're already starting slowly the promotion here for dedicated customers here on the 60 volt part, which is going to come in the first half of next year. And then of course we've got 100 volt also on the schedule here for next year. We're planning more products, but that's for a later webinar because those would be too far out to present already at the moment here. The Q2 2020 MOSFETs, automotive MOSFETs we only released a standard version here. I'll let this slide sink in a little bit more. To be honest with you, they have big die. So if the RT junction to case is the most important parameter, or the avalanche capability is extremely important, do not discount these here. Of course, we are promoting now the split gate technology for future designs here, but please be aware that these are still available here in the old trench technology here. Again, here they go from, let's say, 2.5 milliohm to around 30 milliohm here. This is of course 60 volts here, and so it's 2.5 to 15 in 40 and 5 to 30 milliohm in 60 volt here in the PDFN 5x6 package. And those are also automotive qualified. Let's finish the webinar in the last couple of minutes here with some applications information here. Here we're going to try to link the application information with the process a little bit to do something completely different here. So what we're seeing here on the left is power switch. A lot of people actually use the word load switch here for this, where you just randomly connect or disconnect loads here, depending if you're going on standby and your efficiency and that type of stuff. Of course, ORing, that's usually implies significantly more power here. So what happens is you turn the MOSFET on and off, and that's it. So there are no switching losses to speak of here. So in this case here, if you look at the process here, of course, we want the right voltage for the application, the right combination here, low RDSON, but with the right combination between RDSON and efficiency and cost, of course, because it all comes out of cost here. We may need a high current surge rating here, things like that, and a safe operating area. That's more for ORing if you talk a lot about a lot of power here. So even the market is split a little bit in two, right? I mean, for these simple load switches here, and that's why trench will not disappear here. If you have a lower small die, that type of stuff, there's not much split gate technology you can add really to this application, apart from the fact that you can also do it that way here. So in SOT 23 here, the technology demands are not that special on the MOSFET. It's just a matter of cost more in the supply chain. The other, if we go to the middle now, to the low switching frequency, we're talking about motor control or driving inductive loads. We took a BLDC motor here with 6 MOSFETs to control it, because we want to sell lots of MOSFETs here. But of course, it's what they do have in common here, if it's just a fan or with 4 MOSFETs or something like that, an H bridge here, is that they switch at a low frequency, usually less than 20 kilohertz. So the dominating losses here are also RDSON. So you really want a good RDSON per square millimeter here to compete in this process here. And depending, of course, what type of die size you need. If you're working on a 12 volt battery, you need a lot of current to drive these motors here. So you're going to have big die here. So for that, those big die, of course, the split gate process is optimal and perfect here. If you're having lower currents here, it's not necessarily needed here, because you're going to use lower RDSON MOSFETs. So that is one of the areas you need to take into account here. We're improving the threshold voltage to 1.4 volt here. As you can see, we're going to explain that in the next slide here. You want the high current rating if the motor stalls here, and especially here, if you really have a low voltage and you need to provide a lot of power to this motor, sometimes it becomes more economical to parallel MOSFETs here. So you want this uniformity of the parallel usage. And of course, you can't avoid, if you are in an inductive environment, sometimes the MOSFETs may avalanche, so you want a good avalanche capability, reverse energy dissipation capability here. So that's another important feature of the device here. Of course, we are rectified by company. We're going out to the high switching frequency here. You know, you could also show a buck converter here, but we're rectified people, so we like to show synchronous rectification in this type of application here. And here, of course, the technology is the dominating factor. It's, you know, once you go settle on your breakdown voltage, 40 or 60 volt or whatever voltage you have, you want to have both RDSON low and also the switching losses low here. So this here is key, the figure of merit, and for this type of applications, the split gate technology is completely mandatory. So here we go. Here, let's look a little bit more at these applications in detail. So the next one is on the parasitic terminal of MOSFET here. What you see here on the left-hand side, it's not the sharpest image here, is a nice MOSFET that has got a nice blowhole here. So somebody killed this fan here by stressing the MOSFET here, and we suspect that it's you know, an accidental short circuit might have caused it here. So you can drive a fan or a motor here in two different ways here. This circuit here is called PMOS on the top. It's not very sharp, sorry, here, and NMOS, so I'll read it out here. So it's a complementary thing here. So a fan is maybe not that much power here, so complementary MOSFETs are perfect here in this bridge here. And of course, you can have also here, you know, the motor can be also controlled here by two N-channel MOSFETs if you have a little bit more high power here. So this is the drawing we're going to focus on here, and we're going to look at the gate of this, the bottom MOSFET here, what happens when it turns on here. The formula you see here is an approximation here. It's just a capacitive divider. The voltage on the gate here is a capacitive divider between the two voltages here, between and the drain source. In reality, that this is an approximation. What happens is you have some parasitics somewhere, right? So parasitics here, everywhere in the circuits there are parasitics here. So these do not help in this case. And you also have a DVDT happening here on the MOSFET. So what happens depending on the ratio here, so what could potentially goes wrong is that the capacitive divider here will actually have inadvertently turning on the lower MOSFET here by having a spike over its threshold voltage here. If this is turned on, of course, you get a circuit and you get, you know, you blow up your die here. So that's why we always, and this is why I made this one the bigger one here of the slide here, the bigger lettering here of the slide here. That's why you want to have a good and high ratio of this bottom capacitance to this lower capacitance here. So our process, split gate process, actually provides that. You also need to take into account here that the threshold voltage has a negative temperature coefficient here. So, and also if you start at 1.4 volt, worst case here on the minimum here, you have a little bit more margin here on this gate here to avoid this type of situation than what you would have if you have a 1 volt MOSFET here. So this is one of the process improvements we did, specifically more for power management or for motor control circuits, although this could also happen in other circuits, of course, in the industry. The next slide here that we are showing you is on synchronous rectification here, and some benchmarking with company A and B, and it just shows you that for switching for synchronous rectification here, you know, the performance of all MOSFETs is going to be quite similar here. So with 360 watt here, 30 amps here, so we have a 12 volt output here, and we're using 150 kilohertz here. So what happens here, if you measure the efficiency of your circuit here, you're going to see a similar performance for all companies here, given the fact that their RDSON here is also, we're looking at 2.5 milliohm type of MOSFET data sheet here. So their typical RDSON is also quite similar here. The only issue is that company A here has a slightly higher QGD here in their process, and you're going to notice that here, of course, in the lower power ranges here, because of course, as the load or the loading of the power supply goes down, the switching losses ratio of the switching losses to the RDSON losses are going to increase here. So the switching losses are going to slightly become more dominant than in this part of the power supply. Then of course this is going to punish company A in this case, and you're going to see a minor reduction in efficiency here. So this is some thing here. So this is, we've got a number of other slides here. We're not going to show them all to you, but this gives you an idea here that actually the products we introduced are competitive to have a competitive performance to everybody else that's on the market here with split gate technology. The last thing here is some of the other benchmarking we did and analysis available. We have a benchmarking lab. We have colleagues in Taiwan that are very experienced with the MOSFET designs and MOSFET applications engineering. So we can support you on all applications questions here with our friends in Taiwan here. We did a lot of benchmarking with other people and other people's competitors here. The first thing we did is, of course, on LLC power supplies with synchronous rectification here, where we've done benchmarking products here. We're now doing it, of course, also in buck converters here, where we're going up to frequency of 2 megahertz, which challenge the MOSFETs a little bit more. What you see is that our MOSFETs are competitive here in the normal applications here. We can always talk about something, a PlayStation, where you have to deliver 1,000 amp at 1 volt with digital power and 2 megahertz or whatever. You know, that type of applications here, but you know, your normal application, switching applications, our MOSFETs will be perfectly adequate, and you will see a competitive performance in efficiency when you use our products. So this actually stops it here, the webinar here. We're at 45 minutes. So here I would like to offer a brief summary here. So TSC developed a competitive 40 volt split gate technology MOSFET here. We have an important partner for the front end, UMC. We are investing in the back end here. We've got a supply chain that can meet automotive standards as well as non-automotive standards. We're looking for everybody's business here. We have more process development ongoing here in TSC to further expand our product range here, and of course we will be in the MOSFET business for a long term. So that actually was the last slide of the webinar. I will now go to the chat function and see if I can see the questions here. And I will now go to the chat function. Last time, you don't have to worry if I can't find your question. Last time it was all recorded, and actually we can answer to you by email here. So I'm going to check here because the chat doesn't show up here. Questions here. So I'm going to wait 20-30 more seconds to see if I can see any questions, and then we'll afterwards we'll close the webinar. So I cannot see any questions at the moment here. If I missed them, I'm sorry. I think that the software is not so easy here. So in this case, I would like to say thank you everybody for attending our webinar here. Again, the recording is available, and also the slides will be available to everybody attending here if you wish to share those also with other people. And I wish you, for the people in Europe, a pleasant afternoon. And thank you again for your interest in our products and Taiwan Semiconductor.